Hey guys, here we are, Chapter 15, Section 5, Nuclear Power. We're going to wrap up non-renewable energy with this today, but nuclear power is a lot to it. So hold on and let's work our way through it. First off, nuclear power overall has a very low environmental impact and a very low accident risk. But of course, with everything, it does have its drawbacks. Overall, it's a pretty low net energy yield. We've got to mine the uranium, dangerous process. The uranium has to be processed to get higher grade and yield. And all of this is radioactive, lots of stuff with it. So ultimately, it winds up being sort of a low net energy yield, all the energy going into it for what we get out. High cost, very expensive to build the plants. Mining everything around it is fairly expensive. The fear of accidents, wherever one is, the idea of an accident of radioactive leak and people getting cancer from it and dying of radiation poisoning is very real, and it's a factor that has to be taken in whenever you go to put one in. Not to mention, we have the long-lived radioactive waste. After this stuff is used and it's spent, it's still radioactive, and we have to store it for years, not like tens or hundreds, but thousands of years. And nuclear reactors actually play a role in spreading nuclear weapons technology. As we teach people how to enrich the uranium, able to be used in the nuclear power plants, well, it's only a step away from getting it to weapons grade. So the technology of taking uranium and being able to use it in a nuclear power plant actually winds up giving the technology away in order to refine it to get to weapons grade. So it does have a role in nuclear weapons, which nobody's really a fan of. Now, let's talk about how a nuclear fission reactor works. This is your generic nuclear power plant that you may go to. We're using nuclear fission. We are splitting an atom. And when the atom splits, it releases lots of energy. We talked about this with other chemicals. If you break the bond of alcohol, now that's a molecule, and it's much easier to break a molecule into the separate atoms. Here we're talking about breaking up an atom. When we break apart the atom, it releases enormous amounts of energy. Now, for the most part, we're just going to talk about they're light water reactors, heavy water reactors, but sort of at its core, they tend to be very similar. We're boiling water. So the picture up here is showing a generic insides of a power plant. We put the uranium rods in. This is our fuel. The uranium ore is heating up. The radiation heats the things up, boiling the water, spinning the turbine, creating our electricity. Nothing really shockingly new there. It's just radiation is causing the water boil instead of burning coal or oil or something else. We're just creating steam to spin the turbine. Now, it's fueled by this uranium ore, which is mined from the Earth's crust. Enriched uranium gets packed into these little pellets. Now, a pellet, I should have brought one with me. Well, I don't have a real uranium pellet, but I've got a sample what one looks like. It's really about the size of an eraser head, slightly fat, but it's less than the tip end of my pinky here. Now, that little bit of uranium size, that is more than 2 tons of coal. We get more energy out of a tiny little pinky than 2 tons of coal, which would practically fill this room. A lot of energy packed in a little teeny tiny thing. Well, these are packed into a rod, say about yay big around. And this is what goes into the core, and that's releasing the heat. Now, it's releasing heat through the fission reaction, which I'll go into here in just a minute. And we also have control rods. So we have rods that will absorb excess neutrons giving off, so we can control the reaction, because it's a chain reaction and it heats up and heats up. And if it starts to get too hot, we can put in control rods and control the reaction so we can regulate the heat, because we don't want it getting too hot. If you look at the picture up here, this is what's going on. Now we're looking at it at the atom. Of course, in just one of these little teeny tiny pellets, there are trillions of atoms. Now what we were doing is we were breaking apart uranium-235 typically. So it's uranium-235, meaning it's an isotope. It has a lot of extra neutrons in there. Well, a neutron is fired initially at one of the atoms. When it hits the uranium-235, that atom splits in two. And it typically will split into a krypton and a barium atom. So now instead of having uranium, I have krypton and barium. And when they break apart, it also releases 3 more neutrons that fire out. So you can kind of see in here, it's almost like firing a gun at one thing and it splits in half, but when it does, 3 more bullets come shooting out, if you will. Now this is all packed in really densely in this little pellet, and there are trillions of these things in there. So one breaks apart, 3 neutrons fire out, and those 3 neutrons fire out, everything's packed in tight. They wind up hitting another uranium atom. This uranium atom decays, it breaks apart into barium and krypton again, and then 3 more neutrons fire out, and it's a chain reaction, and it begins firing. And every time an atom is broken to, it releases energy. And this goes on and on until the uranium is, there's no more uranium, and all we're left with is the krypton and barium, possibly some other element, thorium, that it degrades down into. And this creates the heat. So it's a solid bar, and the solid bar just begins to get hotter and hotter and hotter. Now, once again, we can drop a control rod in, which will absorb some of these neutrons and keep the reaction in check or in control, because we don't want it to get too hot. We want it hot enough to boil the water, create our steam, but not so much to evaporate the water instantly and or potentially cause a meltdown. But nuclear fission, that's how it's happening. All we're doing is splitting atoms, but once the process starts, it continues on its own until the uranium is spent. So we have to mine the uranium because we have to have a core of uranium, and it gets used up in the process. Not really like burning a log, it stays the same size, but it is no longer uranium. It is now a solid chunk of barium, krypton, and probably some thorium, because uranium itself just degrades into thorium naturally. Anyway. Water is the usual coolant. We have this thing in here. Power plants are almost always near a water source, and very true of nuclear power, because we need a lot of water to come in and cool. The water is sealed that's going up and spinning the turbine, and we keep recycling that, and that winds up being radioactive water. But what just goes around that whole system is regular water. It goes around to help keep it cooled off, contain it. We have a containment shell around the core itself. This is for protection. Then there is an emergency core cooling system. That's why we need large amounts of water. But because of this, we have to build the system itself. There has to be a very special containment core in case there are any problems. Then we have an emergency core cooling system. Lots of redundancy built in for safety and protection. It costs somewhere between $9 and $11 billion to construct a nuclear power plant. That's if we're just going to take the plans of this plant that we already know how to do and build it over there. If we're looking to change anything, upgrade it, go into new advances, then the price tag just starts going way up. Now, the United States, France, and Russia were the leading producers of nuclear power in 2014. However, China is seriously upping its use of nuclear power. They have plans to pull a lot of nuclear power reactors online in the future, but once again, currently, it's these nations that are doing it. Now let's talk about the nuclear fuel cycle. Overall, nuclear fuel is very clean. Once it's burning, it's just heating up the rod. We're not burning anything, so we're not releasing any carbon dioxide. So once the nuclear reactor is online and running, it's incredibly clean. There's no pollutants going into the air, there's no carbon dioxide going into the air, there's nothing. We got radioactive waste we have to deal with, but the actual running of the plant is perfectly clean. And it tends to have a low impact because we were just mining the uranium, and typically mining the uranium is not as usual in strip mining. It can occur, but it takes a very small amount to last a really long time. Once again, one teeny tiny pellet size of an eraser is enough 2.5 tons of coal by comparison. So it doesn't take as much to get a lot of energy out. But we do have to mine the uranium, process it, enrich it, because we're getting ore, we've got to refine it, get it into it enriched. We use it in our reactor, and then we have to safely store the radioactive waste, and then we have to retire the worn out plant. We have to store the high and moderate level of radioactive parts, the stuff that has been containing the radioactive. Well, that metal, those parts around it are now also radioactive, and they have to be stored. And your typical plant can last 50, 60 years. A lot of these were started, I'm gonna say the 80s, late 80s. So it's not long before we have to begin. We've already retired some, and we're gonna have to begin retiring others, and then we have to store these parts. So the cycle, this is why it winds up being very expensive. It's not just mining the uranium, it's mining it, enriching it, building the sites, storing the waste, decommissioning, and then storing parts of the cycle. And as we talk about anything, the trade-offs, the advantages. Once again, low environmental impact. It emits 1/6 the amount of CO2. We're going to talk about it's not CO2 free because all the process of getting the uranium, manufacturing the uranium, refining the uranium, building the power plant, all of this is causing CO2. We're having to burn and do a lot of fuel to get to it. Once the situation is up and running, it's CO2 free. But the whole process isn't, because we're having to use other processes to get to it. But uses a lot less CO2. Low risk in accidents. We have a lot fewer risks and death with this than we do coal, oil, mining, everything else. They tend to be fairly dangerous work. Of course, it's a low net energy. By the time we put all the cost and effort into it, we're not getting as much energy out because of its high overall cost. We have the really long-lived waste, and it does promote the spread of nuclear weapons. So the advantages are good, the disadvantages are pretty serious, things we really have to address. When it comes to the radioactive waste, those rods, so we have a rod, say about the size of a Coke can, but about this tall. The rod has to be replaced about every 3 to 4 years. So one rod does energy for 3 to 4 years, powers an entire city like Gainesville for 3 to 4 years, one single rod. So it's an amazing amount of energy in one rod. But then we have to store it. This thing is radioactive, and it has to be stored anywhere from 10,000 to 240,000 years, thousands. Our country's only been around for a few hundred, and we're talking about having to store something for 10,000 years. It's really difficult to come up with a way that you can do that and it be safe and have any idea of the future of where the site is going to remain safe. So this is a big deal. Typically what we do is we take the rod out and it gets stored in water for several years to cool. So it goes down in the water supply, sits there to cool for several years. Once it's cool, because once again, we've spent most of the uranium, that's why we've had to pull it out, and it's down there cooling off. Then we'll transfer it to a dry cask, something that's dry, encased in cement. And then it can be processed to remove any of the plutonium that may be in it. And the reprocessing reduces the storage time, once again, from just 200,000 down to about 10,000. But it is very costly, and this is what produces our weapons grade plutonium. And unfortunately, there are no permanent secure repositories. This was the idea. We'll have it, and then we'll create a secure depository for it, somewhere we can put it, bury it deep underground where it'll be safe and away from anybody. We started one in Nevada in the Yucca Mountains. and that site has been abandoned. Political pressures, cost has gone up tremendously, wanting it there. Once again, if we put it deep down in the ground, it's reasonably safe, but if we have earthquakes or faults or other problems and it cracks open, it could be a hazardous waste site for centuries. We don't have one, so everything is now being currently temporarily stored, typically near where the radioactive plant is. We simply don't have a permanent, secure repository, a place to put it. We're leaving it to future generations to figure it out. Also, just retiring the nuclear power plants has an enormous cost. You got to break everything down. We got to take everything that's radioactive, break it down, and it has to be stored as well. Now, typically, if you kind of look at the picture back here, on the left-hand side, you can kind of see the guy with a big pole like down in the pond. Well, this is the water retention. That's where it's stored temporarily, 3 to 4 to 5, sometimes going up into 10 years because it's sitting there. And then after it's cooled off completely, then it gets stored into something like on the right there. We put the spent rods inside of there. That thing is put in a encased core. Then we pour concrete around this. And this is ideally what would then go to a permanent repository. But of course, we currently do not have a permanent repository that's going to store it for the 10,000 years or so. Now, with nuclear power and climate change, once again, once the power plant is running, there is no CO2 emissions. But in the nuclear fuel cycle, if we talk about it from getting it to storing it, there is carbon dioxide emitted. It's much less than burning coal or even burning oil, but it exists in the mining, machines running to mine it, machines running everywhere else. Once it's up and running in the plant, it releases no CO2. So it's very true that nuclear energy burns clean, but it's false to say there's no carbon dioxide footprint because it takes a lot of energy before we can get it into the rod. Now, nuclear reactors produce about 20% of the energy in 2017 in the United States. There are 59 new nuclear reactors that are under construction worldwide, at least as of 2018. And currently, at least in the United States, it's true of most countries, the government is providing subsidies, tax breaks, and special insurance for the nuclear industry. It's just too expensive for a state or a local area to take on. It takes federal funding to create them. And of course, some of the accidents have really dampened public confidence. We had 3 Mile Island in the United States. There was Chernobyl in Russia, and obviously back in 2011, the Fukushima accident with the tsunami that took some out as well. If you look at the chart behind us, you can see 1970s is when we began to bring them up. Through the 80s and 90s, we had steady increase of nuclear power, and then it's kind of leveled off. We're not really building new plants. We're not really building more online. The research and the cost as everything has gotten just so expensive. There are some ideas for how to make it cheaper, some of the new technologies, if you will. We talk about these advanced light water reactors, which have a lot of built-in safety features, so we don't have any problems. There's an idea of building them that are smaller and modular, something the size of like a container that could be brought, say the size of a school bus, that could go here or there. It could be modular and moved around. They're not yet built, but it's being evaluated as a possibility. And then there's an idea of using thorium-based reactors, which would be a lot less costly and safer. Of course, these are new technologies. They're not out there yet, and it takes a lot of funding to get, a lot of research and development to get these online. So the idea of spending millions or even billions of dollars in research to something that might never even come to pass is kind of difficult to stomach, especially when we have other avenues. Once again, instead of spending the $1 billion in research into nuclear, that money can be spent on solar and wind, some geothermal, some other things that are right here that don't have as much in the downside. Some of the solutions that have to be looked at. For us to really think about nuclear energy long-term as really being a real source, like once again, 20% in the US, give take, but for us to think about it being more, well, they have to be built so that runaway chain reactions just can't occur. The fuel methods of fuel enrichment need to be such that they don't lead to nuclear weapons. They need to have a way to do it that doesn't lead to getting it high enough grade to be used in weapons. The spent rods and the dismantled plants need to have somewhere that it can be disposed of without burdening for future generations. Right now, we're kind of saying, okay, it's up to you to figure out our problem. We created all this nuclear waste, but we don't know what to do with it. We need to know what to do with it before really continuing on. We need to take in the entire fuel cell option. We talk about it's clean energy. It is, but we need to address the entire thing. Just talking about how wonderful it is that this tiny little section of it isn't quite right, because we have the whole process to get there, and then we have to deal with the waste afterwards. So the entire fuel cycle has got to generate fewer greenhouse gases than it currently is for us to really look at it and talk about it being as clean as we say it is. Let's take a look at a case study, the Fukushima Daiichi nuclear power plant. This was back in 2011. Earthquake off the coast creates a tsunami. So March 11, 2011, the offshore earthquake, tsunami comes in, wipes over the plants. Well, the water comes in, damaged the diesel pumps, which were circulating the water. The water was used to cool it off. When it stopped cooling off, hydrogen gas built up, hydrogen gas exploded, blew the ceilings off of some of them, and the waste began to melt down. As the waste began to melt down, some of it released into the coastal waters. People from that area were evacuated, moved out. Now, we didn't have deaths associated with the plant, but this was more of a local problem. It really was not a regional or a global. It was really just that area of Japan that we had the issue. But there were some very important side effects, if you will, from it. It increased the fear about nuclear power. Quite a few countries after that decided to take all of their power offline and put their money not into nuclear power, but into more of the renewable resources. Germany, a few, and France as well began looking at decommissioning rather than starting to build more. It revealed a single accident. This single accident, something, an act of God, tsunami, something that couldn't be controlled, cost somewhere around $500 billion. We talk about 9 to 11 billion to build it. Well, a $500 billion price tag to try and fix a problem is huge. And because of this, once again, more countries began phasing out, and it actually spurred Japan to reduce their energy use. They became a lot more efficient as a country, realizing, hey, we don't want to rely on this energy source. We need to be more careful about our use. Another idea that we're talking about, or has been talked about, it seems like forever, is nuclear fusion. This is what is happening on the surface of the sun. Hydrogen and hydrogen get fused together because of gravity. It squishes them together in the core of the sun, and when they fuse together, it releases massive amounts of energy. Fission, we take something and it's breaking apart, eventually it's gone. Fusion, theoretically, could go on forever. If we could have a contained fusion reaction inside of a plant, well, it could generate energy, theoretically, forever, as long as we can supply the raw materials like hydrogen, which is in immense quantities. But the technology is very difficult to develop, and no approach has actually produced more energy than it's used. In other words, we're putting more energy into the process than we get out, so it's a net negative energy. So when something's a negative net energy, we're really not interested in it. Once again, if it costs me $1,000 to get, $500 worth of energy, it's just not worthwhile. So fusion might be an answer sometime later in the future, but right now we haven't come up with a way to develop it that doesn't take more energy than we get out. So when we talk about these things, the big idea is net energy. We're looking for high grade as opposed to low grade, and definitively we don't want net, like if you're trying to get hydrogen. Currently, it takes more energy to make hydrogen than we get out of it using it as a fuel source. So our conventional oil, natural gas, and coal, a lot of it, but moderate to high energy yields, but that really high impact. We talk about nuclear like we did. There are the benefits, low environmental impact, low accident risks, but the downsides are the cost, and when we do have accidents, they tend to be truly horrible. Guys, that wraps it up for non-renewable energy. Take care, and we'll see you next time.